So if you take a standard room full of, I don't know, 10 perfectly normal people, right? And a billionaire happens to stroll in and order a drink, the quote unquote average wealth of every single person in that room just shot up to over $100 million.
Right, which is mathematically a verifiable fact,
But practically it's a complete lie. I mean, no one in that room suddenly became a millionaire just because one guy walked through the door.
Exactly. And that phenomenon right there, that's why the very concept of the average is just so incredibly dangerous if you don't know what's happening, under the hood.
Yeah.
We're completely conditioned to treat that word, average, as this unmoving anchor, like it's the definitive center of gravity.
Yeah, but it really isn't an anchor at all. So today we are taking a deep dive into descriptive statistics, and whether you're, actively prepping for your TEAS or your HESI and nursing entrance exams, or you're just insanely curious about how math secretly manipulates our reality, this is your shortcut to mastering the numbers that run the world.
Really is.
We're going to unpack the mean, the median, the mode, and the range. We'll look at how to compute them and interpret them, obviously. But more importantly, we're going to explore why relying on the wrong version of average can lead to massive real-world consequences.
Yeah, especially in fields like healthcare. But to understand how these numbers can distort reality, we have to start with first principles. We really need to establish what these tools are and, mathematically, why they behave so wildly differently from one another depending on the actual data you feed them.
Right, so let's start with the most common one, the mean. I mean, this is what you probably think of when someone says average.
Yeah, it's a classic one.
The computation is super simple. You take the sum of all your values, and you divide that by the number of values you have. So if a nurse wants to find the typical heart rate of a patient over a shift, they add the readings up, divide by the number of readings, and boom, they have the mean.
But as we established with the billionaire in the bar earlier, the mean has a fatal flaw. It is incredibly sensitive to extreme anomalies.
Because it just drags the number up.
Exactly. So if one of those heart rate readings is a massive spike, the mean gets yanked upward. If we want a tool that resists that kind of distortion, we calculate the median instead.
Which is literally just the middle value, right?
Yeah.
You take all your data points, you sort them in numerical order from smallest to largest, and you just find the one sitting dead center.
Yep, that's it.
Though, if you have an odd number of data points, it's that single number in the middle. But if you have an even number, you just add the two middle values and divide by 2.
Right, and then you have the mode. Now, the mode kind of abandons the idea of adding or sorting entirely. It is simply the value that occurs most frequently in your data set.
So it's just a popularity contest?
Basically, yeah. If every number is unique, you have zero mode. If one number repeats the most, it's unimodal. If two numbers tie for the most frequent, it's bimodal, and so on.
Okay, so mean, median, and mode. But the fourth term we always hear grouped with these is the range. And I know I calculate that by taking the absolute maximum value in a data set and subtracting the minimum value. But I actually have to stop us right here and challenge this grouping.
Oh, go for it.
I know these are always taught together in schools, but the range doesn't belong in this list, does it? I mean, the first 3 are trying to tell you where the middle of the group is. The range is just taking the highest and lowest numbers. It tells me absolutely nothing about the middle.
You've hit on a massive point of confusion for a lot of students there. You are completely correct to separate them. Mean, median, and mode are measures of central tendency.
Right.
They are essentially different philosophical answers to the question, what is a typical value here?
Sure.
The range is not a measure of center at all. It is the simplest measure of dispersion.
Dispersion, meaning spread.
Exactly. It exists to answer a totally different question, which is, how spread out is this data?
Yeah. So we have the spread, and we have 3 ways to find the center. But let's dig into that mechanical difference between the mean and the median. Like, why does the mean get yanked around by outliers so aggressively while the median just, completely ignores them?
It fundamentally comes down to how each formula mathematically defines distance. The mean has this very specific mathematical property. It is the single number that minimizes the total squared distance to every single point in the data set.
Wait, why are we squaring the distance? If I want to know how far apart things are, why not just measure the actual distance? Squaring it seems like you're intentionally making the math overly sensitive.
Well, it does make it sensitive. That's exactly it. Because when you square the distance, extreme values gain this massive gravitational pull.
Oh, I see.
Think about the math for a second. If a normal data point is 2 units away from the center, squaring it makes its pull 4. But if an outlier is 10 units away, squaring it makes its pull 100.
Right. Wow.
Yeah, so the farther away a point gets, its influence doesn't just increase, it multiplies exponentially.
So visually, I'm picturing this for you listening. Think of the mean as a highly elastic rubber band connecting all your data points together. If one data point suddenly unhooks and runs a mile away, the tension from that stretched rubber band drastically pulls the center point right along with it.
That is a perfect analogy.
The mean has to follow the outlier because of that squared tension.
It perfectly captures the mechanics of it. Now, the median, conversely, operates by minimizing the total absolute distance. There's no squaring at all.
Which means no rubber band.
Right, no rubber band.
So the median is just like someone pointing at the middle person in a physical lineup of people organized by height. The tallest person at the very end of the line could step 5 feet away or 5 miles away, and the person pointing at the middle of the line doesn't move their finger at all. The middle person just doesn't change.
Exactly. Which brings up a really fascinating historical question.
Yeah.
Why do we have these vastly different ways to calculate the middle? I mean, it wasn't an accident. Historically, scientists are trying to solve vastly different problems, and the tool you use depends entirely on the physical reality you were trying to measure.
So where did the mean come from then? Like, who decided we needed to minimize squared distances?
Astronomers.
Really? Astronomers.
Yeah, specifically mathematicians like Adrien Marie Legendre and Carl Friedrich Gauss back in the early 1800s.
Yeah.
They were trying to track the exact positions of stars and planets.
And observing stars through, 19th century telescopes has to involve a massive amount of noisy, imperfect measurement, right? Like atmospheric distortion, human error, all of that.
Exactly. When an astronomer is combining 50 noisy measurements to find one true star position, they want a method that factors in every single observation to cancel out the tiny errors. Because the mean minimizes those squared deviations, it pairs flawlessly with what is called the method of least squares. It basically became the gold standard for physics.
But the median comes from a completely different world. It wasn't the astronomers, it was the sailors.
Yes, the sailors. In 1599, an English mathematician named Edward Wright suggested it for sailors taking compass readings at sea.
Makes sense. It's pretty rocky out there.
Exactly. He essentially noted that one wild compass reading could ruin your entire navigation if you average it in. He said, just take the middle reading. And later, around the 1750s, Roger Boscovich used a method to fit lines to data that minimized absolute deviations, which mathematically defines the median.
But for a long time, the median was viewed as this second-tier statistic, right?
Yeah.
Just a crude substitute you use when you were too lazy to calculate the mean by hand.
Oh, absolutely. It was looked down upon for over a century, but made a massive comeback in the 20th century because statisticians realized the median is usually the superior choice for messy human data.
This brings to mind that famous story about the wisdom of crowds. Francis Galton at the livestock fair. Does that demonstrate why the median works so well for human data?
It is the ultimate proof of it, yeah. In 1906, Francis Galton attended a fair in Plymouth, England. There was a contest where 787 people submitted tickets, guessing the dressed weight of an ox.
And these were farmers and butchers, but mostly just ordinary spectators, right? Like with no real expertise.
Exactly, just a random crowd. Galton collected all 787 tickets. And instead of calculating the mean, he calculated the median guess.
The exact middle guess of nearly 800 people.
Right. And the median guess came out to 1,207 pounds. The actual weight of the ox was 11,198 pounds.
Wow, that is incredibly close.
The crowd's median estimate was off by less than 1%. It beat the individual estimates of almost every professional butcher at the fair. So Galton published this finding, proving that the median can effectively distill a baseline truth from a chaotic crowd.
That's wild. Okay, so the astronomers gave us the mean, the sailors gave us the median. Where does the mode fit into this history?
The term mode was coined much later, actually, in 1895 by Carl Pearson. He was studying asymmetric distributions and needed a term for the most popular value. He borrowed from the French word mode, meaning fashion. It is simply the most fashionable value in your data.
The most fashionable data point. I love that. Well, let's bring these concepts out of the 19th century and onto the modern hospital floor. Because understanding these distinctions isn't just an academic exercise. If you're going into nursing, this is literally life or death. Galton's ox shows how a group can hone in on a truth, but what happens when you are tracking a single individual's baseline in a high-stakes clinical environment?
This is where understanding the math dictates whether you catch a patient in decline or entirely miss the warning signs. Let's look at vital signs. Imagine you're recording a patient's temperature over your shift. Most of the readings are hovering right around 98.2 to 99.1.
Pretty normal.
Right, but suddenly there is one solitary spike to 101.3.
Okay, let's run the math on that. If a doctor just looks at a chart that calculates the mean of all those temperatures, that 101.3 spike pulls the mean up to, say, 99.0. And a 99.2 average just reads as mildly elevated. It completely obscures the fact that the patient actually spiked a fever.
But if the chart displays the median or the mode, they both stay anchored down at 98.6. The mean gets dragged by the fever, but the median represents the patient's true baseline status for the vast majority of that shift. This highlights why trending vitals manually over time is so crucial, rather than just trusting an automated average.
That is that rubber band getting pulled by the outlier.
Yes.
But it gets truly terrifying when we look at lab values. Take the example from our source material regarding serum potassium levels. Imagine you have 5 patients on a floor. You pull their potassium levels 3.5, 3.9, 4.0, 4.2, and one patient comes back at 9.8.
Think about the physiological reality of that. A potassium of 9.8 isn't just high. That is imminent cardiac arrest.
Right.
That is a lethal outlier.
But look at what happens if someone poorly summarizes this data. If you take the mean of those 5 patients, the sum is 25.4 divided by 5. The mean potassium level for the floor is 5.08.
And a 5.08 just looks like the group is borderline hyperkalemic. Mildly elevated, not an emergency at all.
The mean takes that lethal 9.8 and smears the danger across all 5 patients. It literally hides the one person who is actively dying. But if you sort them and take the median, the middle value is 4.0. The median correctly shows that 4 out of the 5 patients are totally fine, which forces you to look at the raw data and find the one acute anomaly.
Averaging away a critical outlier in a clinical report isn't just a math error, it is a profound patient safety failure. The tool you use dictates the reality you see.
So true. Both of those examples use numerical data, though. What if the clinical data has no numbers, like admitting diagnoses or blood types?
That is exactly where the mode becomes the only tool left in the toolbox. It is the exclusive measure of central tendency for categorical data. Data with no natural numerical order.
Right, because if an ER draws blood from 7 patients and the results are O positive, A positive, O positive, B positive, O positive, AB negative, and A positive, you can't add O positive and B positive together.
No, you definitely can't.
You can't sort them from smallest to largest either.
But you can immediately see that O positive appears 3 times. It is the mode. And if you are running the hospital's blood bank, knowing the most frequent blood type coming through the doors is the exact intelligence you need to manage your inventory.
So we can clearly see how the wrong quote-unquote average distorts a medical chart. But that exact same distortion is weaponized every single day in the media, in education, and in economics.
Oh, constantly. It happens the moment data becomes skewed. If you have a perfectly symmetric bell curve, a normal distribution, the mean, the median, and the mode are identical. They sit perfectly on top of each other right in the middle of the bell.
But the real world is almost never a perfect bell curve, is it?
Rarely. Real-world data skews. It leans heavily to one side, and when that happens, those 3 measures get pulled apart. Income is the classic example we see debated in the news.
Yeah, income distributions are intensely right-skewed. You have the vast majority of the population clustered in a moderate earning range, but then you have a handful of billionaires who stretch the right tail of the data infinitely outward.
Just like our billionaire in the bar from the start of the deep dive. The top 0.1% pulls the mean artificially high. That is why the U.S. Census Bureau deliberately features median household income as its headline statistic.
Because it's more honest.
Exactly.
Yeah.
The median offers an honest look at a typical family's reality. The mean would just trick the public into thinking everyone is vastly wealthier than they actually are.
Hospitals do the exact same thing when they benchmark length of stay, right? It's the same skew.
Yes, length of stay, or LOS. Most patients come in, stay for 2 or 3 days, and go home. But a few incredibly complex, tragic cases might stay in the ICU for months. Those outliers drastically inflate the mean. Healthcare administrators have to report the median length of stay to accurately benchmark how a unit is functioning day to day.
If we are talking about skewed realities, we definitely have to talk about the Lake Wobegon effect, because this is where the misuse of the word average gets almost comical.
Oh yeah, named after the fictional town where all the children are above average.
Right. So in 1987, a physician and researcher named John Jacob Cannell exposed this massive scandal. He discovered that all 50 U.S. states were officially claiming that their public school students scored above the national average on standardized tests.
which is mathematically impossible.
You cannot have 100% of the country above the center.
No, you can't.
It exposed this massive system of grade inflation and outdated norm referencing. It proves that any time an institution claims their numbers are above average, you have to demand to know exactly how they are defining the average.
That's the perfect transition to a very famous, very dark joke used to teach statistics.
Oh, the 3-foot river.
Yes.
The cautionary tale. A man drowned crossing a river with an average depth of 3 feet.
It is grim, but the mathematical lesson is non-negotiable. It brings us completely full circle back to the range. The mean tells you absolutely nothing about variability.
Right. A river that averages 3 feet deep might be a perfectly flat, paved canal that is 3 feet deep from bank to bank. Or it could be 6 inches deep for most of the crossing with a sudden, unexpected 9-foot trench right in the middle.
If you only know the center of the data, you are flying blind to the danger. You must always pair your averages with a measure of spread. You have to know the range to know if you are about to step into a 9-foot drop.
So if average is such a squishy, deceptive term, let's lock down the ironclad truths. Let's run through some rapid-fire misconceptions for anyone taking their exam soon. First misconception. Average always means the mean.
False. It is an ambiguous synonym. In everyday language, it could mean mean, median, or mode. On a nursing exam, they must specify which calculation they want.
Okay, second misconception. If I have a data set with an even number of values, the median will always be one of my original numbers.
False again. With an even count, you average the two middle numbers. That calculation will often result in a brand new number that doesn't exist anywhere in your original raw data.
Third misconception. Every single data set has a mode.
False. If all the numbers in your data set are completely distinct and unique, there is no mode at all.
Okay, here is the ultimate mind bender from our research. The ultimate aha statistic that proves how weird the mean can be. Are you ready for this?
Let's hear it.
The average human being has slightly fewer than 2 legs.
It sounds like a riddle, but it is mathematically flawless.
The overwhelming majority of the human population has exactly 2 legs. 2 is the mode. 2 is effectively the median. But a small number of amputees pull the mean slightly below 2.0. So the mean number of legs is something like 1.999. It is the perfect illustration that the mean can be a number that describes almost nobody in reality.
Yeah, nobody has 1.999 legs. And that bizarre reality is why statisticians don't just stop at these 4 basic tools. The range, as we said, only looks at the 2 extreme endpoints. It completely ignores everything happening in between.
Right.
As you advance in statistics, you will move to tools like variance and standard deviation, which measure dispersion using every single data point. Or the interquartile range, which measures the spread of just the middle 50% of the data, making it resistant to outliers, just like the median.
So bringing this all together, mean, median, mode, and range. They are not just abstract math equations to memorize for a test. They are deeply embedded in patient safety. They dictate medication dosages. They shape how we interpret everything from real estate prices to CEO pay ratios.
The single choice of which measure of center is used can completely flatter or completely distort the underlying truth of a situation.
So for you listening, here's the real takeaway. Next time you see a statistic in a headline, whether it is the, quote, average recovery time for a new drug or the average test score in a school district, you now have the tools to pause and ask, wait, is that the mean or the median? And what are they trying to hide by choosing that one?
Exactly. And as we navigate the modern world, I'll leave you with this final thought to mull over. We're rapidly entering an era where algorithms and artificial intelligence are making massive automated decisions about our lives, who gets a loan, who gets a hospital bed based on massive data sets. What happens if those AI models are quietly trained to optimize for the mean outcome rather than the median?
Oh, wow.
Who are the vulnerable outliers in our society that get entirely erased when a computer just averages everything out?